In progress. There we go. All right. Now you do what you're supposed to do here. Don't argue with me. Know why everything
I
wants
get
to
so
be.
angry at technology. Like, what are you doing?
Well, I already had a problem with the TV this morning and I couldn't make that work. And Jason was on a bike ride and I was panicked because when I can't figure it out because he has like just all kinds of crazy settings, and they all go through a receiver and I understand that part, but it just didn't seem to want to do what it was supposed to do. So anyway, all right, let me try this again. It's opening up my app. It's just being like real picky today. Here we go. Oh, that's promising. Yes. Yes, your lab teams will change. All right, so we should be good to go. Here we are. All right. Sorry that took a bit. That was a little funky. Yeah. It's funny. Sometimes I find something, like in this case, I found that and I just wanted to keep using it. So I just stuck, the whole slideshow is kind of pink, but it's pink because that first slide, I just like that image. So then there it is.
And also gold for Tinker Day.
Little gold for Tinker Day. And who knew? I didn't know it was going to be Tinker Day. Ta-da. Okay, so.
Your apple. Look, you got
the apple green. I know, I got the green and gold everywhere. So anyway, you'll get your brownie and you can have your donut too when it's time for a lab. We'll do all of it. Woohoo! All right. It's supposed to be like 40 something in Roanoke today too. They're gonna be cold. So we're doing forces and fluids. We have one more lesson after this and we will have wrapped up this unit and then we are moving on to Q2 and units 4 and 5. So we're gonna talk about pressure today. Pressure. All right, pressure. Pressure is the result of something over something. Oh boy, everybody's waking up this morning and getting out their binders. Oh, and by the way, this is One-Eyed Wilhelm. So
the best name,
right? So anyway, models, like anatomical models, are crazy expensive, and I've been looking for some for years for like when we do biology, and they're usually like $500 to $700 for a skeleton, and I found him for $100 on Marketplace, and we had a little cushion in our budget, so I went and got him. I drove all the way down to Atlanta and got him. So he's an actual anatomical model. He's not like a Halloween prop. He's a real. So if you want to see where your bones are, his are absolutely accurate top to bottom.
Well,
and
what are those like? Why is some of it see-through?
This is where you have cartilage.
Some of our ribs are cartilage?
Yeah, right there in the front. So anyway, I named him Wilhelm because that's the first name of the guy whose full name I can't remember, who discovered the X-ray. And then it works perfectly because, my favorite movie is what? Goonies. And the pirate in Goonies is, who are they looking for? Treasure.
Wilhelm.
One-Eyed Willie. So he's One-Eyed Wilhelm. You got it?
I call him Willie.
All right. Yes, ma'am. You got it? Force over area. Very good. All right. So pressure is the result of force distributed over an area. So to calculate it, you divide what by what, Eunice? You divide force by area. Because when you think of this one's really easy to remember. If pressure is force over area, if I take a force from my hand, put it on this area and press, then it's force over area. So when you write the equation, it looks like force over area, exactly the way you would think, right? That one's easy. This one, you don't have to like try and think real hard. It's right there. It's kind of like when you do speed, when you say miles per hour, then you know that it's miles divided by hours or kilometers divided by seconds, however you want to do it, right? So then fluid pressure. So pressure is measured as, what were you going to say? Go for it.
Pressure is measured as P. No.
You're getting there. Do you know what you're looking for there? What you got, Darcy?
1m/m2. 1m/m2.
Yeah. So yes, it's newtons over meters squared. And it looks like this. So the unit is called a Pascal.
Oh, like that little chameleon thing.
Yeah, Pascal. Yeah. Okay. So Pascal's the one in is it Tangled?
Yep.
Yes. Okay. So Pascal. So why is it called Pascal? It's called Pascal because of a dude named Blaise Pascal. We're going to learn about him because he's very cool. So what is a substance that flows and assumes the shape of its container, Carlos?
Fluid.
A fluid is a substance that flows and assumes the shape of its container. So what two states of matter? Go for it, Nico. Yeah, liquid and gas are both fluids because they both assume the shape of their container. So the difference between a liquid and a gas is that in a liquid, the molecules are more densely packed than in a gas. You can put pressure on liquid, you can put pressure on gas, and it's going to react similarly because they're both fluids. Yes, Miss Emma?
In Mythbusters,
Mm-hmm.
they say that they can use water for like the waves of that would come off like a ball.
Yeah,
They use that
Mhm.
in an episode that I
because it's a fluid. Exactly. So all of the forces exerted by individual molecules in a fluid add together to make up the pressure exerted by the fluid. So here they are. This is how they look, right? You have a fixed shape and a fixed shape and a fixed volume. Oops. Go away.
Why is it
Okay.
lowercase d?
It's actually a capital, but it's just kind of weird. So you have solid, a liquid, and a gas. And that should not, these should, I didn't fix those. Whoops. I got so solid has a fixed shape and a fixed volume. This should say a liquid has no, oh, wait a minute. I didn't do it wrong. Hang on. Hang on. I didn't do it wrong. I'm messing myself up. Let's do it this way. Does a solid have a fixed? Oh, son of a gun. This is going to make me nuts today. I don't know why it keeps doing this today. I'm going to spend the day fighting this and it's going to annoy me to death. Okay, it's going. Dee-da-dee-da-dee. Oh, all right. Let's try this again. All right, go away. Here we go. So this little box is a solid, right? So does a solid have a fixed shape?
No. Yeah.
Yeah, it
Yes.
does. And does it have a fixed volume?
Yeah.
Yes.
Yes, it does. All right. And how about the liquid?
No.
No.
No fixed shape, right? Takes the shape of its container. And how about a volume?
No. Yes.
What do we think?
Yes.
Yes. Okay. It does have a fixed volume. Now you can change the volume if you squeeze it really, really, really hard, or if you put it in a vacuum, but at like 1 atmosphere, kind of, normal earth conditions, it doesn't do that. Okay. Gas, fixed shape?
No.
No. Fixed volume?
No.
Very good. No fixed volume. It scooches all around. All right. So air pressure. The pressure exerted by air around us is called, yes, Eunice?
Atmospheric pressure.
Yeah, atmospheric pressure or air pressure. Air pressure has mass. Okay. Air has mass. So gravity acts on that mass. So when gravity, as gravity acts on that mass, it exerts force over the surfaces on which it presses. This includes land and you. So pressures will balance. Fluids will move from areas of high pressure to areas of low pressure until a balance is reached. Okay, so if you blow into a balloon like we did last week, right? And you stretch that latex into the balloon and you're putting like lungs full of air into that small space, you've now put that fluid, that air, under pressure, right? And what happens if you let go of it?
It will fly.
Right, because what's it trying to do? What's happening with the pressure there?
It's
Mhm.
releasing the
Yeah, it's trying to balance the pressure. So it's trying to make the pressure inside the balloon the same as the pressure outside the balloon. And that is the case when the balloon is just laying on the table and there's a normal amount of air just in it before you blow it up. And when you use a can of bug spray or hairspray or any of those aerosolized cans that you that is air in there under pressure. So
We had so many mosquitoes. We had the
Yes.
raid. We had the off. We were going,
yes. So when you push that button, it allows for that gas to come out because that fluid is under pressure. So anytime you hear like anything you use that tires or pumps and you hear that sound where you hear the air moving, that's just air trying to balance pressure. Now, if you are on the tippy top of a mountain like this guy, what is the air pressure going to be like for you up there versus if you're hanging out at the beach? Carlos, do you know?
higher.
Higher air pressure where? At the beach or on the mountain?
No. No.
On the mountain? Okay. So,
Lower because you're closer to the
Yeah, lower air pressure.
yeah, okay.
Because
So-
when an airplane, like when it drops the oxygen mass, that means you have low
Yes,
air pressure.
very
And
good. So here's why. If you understand why, then you'll never be confused again. So right where you're sitting right now, imagine that you've got a tube, like a column that on your head that goes straight up. Okay. And it's just lets air in straight up. If you're on the beach, you've got you're on the beach. Beach is low, right? Mountains high. So if you're on the beach, you've got that whole column of air. You're lower down. That column is now taller when it reaches the atmosphere, right? And it's full of more air molecules. Where if you're on the mountain, that little column is shorter and there's less air molecules. So when you're at the top of a mountain, you've got lower pressure than when you're at the beach, when you've got higher pressure. So air pressure is also affected by elevation. And likewise, what other kind of pressure is going to be affected by depth, Emma?
Water pressure.
Wait a minute, ask Emma. Yeah, you're right, water pressure. Yes.
Well,
Uh-huh.
I went to Alabama,
Mm-hmm.
to the coast for a homeschool camping trip.
Yeah.
So like
Sorry. I turned that on earlier, so Jason
So
come.
dramatic.
I know.
we got to show stuff. They showed stuff that would like use water pressure to make clouds.
Yes. Okay. So
It's all about
anybody ever swim to the bottom of a pool and then suddenly your ears super hurt and you have to come back up? Yeah. What's happening? Why is it happening?
pressure.
Miko?
because the pressure. There's more water above you pushing down.
Yes. Just like when
That's
you're on the
how it's
beach and
so-
there's more air pushing down. When you swim down in the water and you go down low, yeah, you get more air pressure and you've got air inside your ears, right? So you've got space in there. And what's happening is all of that pressure is increasing and it's like squishing on your eardrums and it hurts. Yeah.
That's how the submarine crashed. It got so low
Yeah.
that it just went.
Boom. Just imploded. Uh-huh.
I was actually talking about that yesterday.
The submarine. Mm-hmm.
Or not the submarine, that ear stuff.
Oh, okay.
My reading teacher.
Mm-hmm.
And we were like, if you have a hole in your ear, you can breathe through your ear.
Yep. So my grandfather was a submarine captain in World War II. So he was Canadian, so that made him part of the British Royal Navy because, Canada, Britain. So he was a British Royal Navy submarine captain. And one of the stories, actually, I have a whole book. What's upstairs? I have a whole book where my cousin interviewed him for weeks and weeks and tape recorded all these conversations and his mom typed it up. It was pretty cool. But one of his favorite stories to tell was about the galley cook, the baker, and he was making bread. They were way down under in the ocean. He made a loaf of bread, but he hadn't baked it yet. You know how when you make bread, you have to let it rise, right? So he had the bread and they were down under. And even though there are things in a submarine to kind of equalize that pressure, it's still more pressure. And the bread just wasn't rising. And when they surfaced later that day and went down to the kitchen, the bread was everywhere, boom, it went everywhere because all those little tiny bubbles in it, that pressure suddenly released and those air molecules within the bubbles could just spread out and then poof, it went all over.
So when someone bakes something so long that it just explodes their oven.
Yeah. So as elevation increases, air pressure
Lower.
decreases as you go up, right? As you go up, it's going to decrease and then it's going to increase. Okay, so we call a relationship when one thing goes up and the other thing goes down, we call that relationship inversely proportional. Inverse meaning opposite, but proportional meaning as one goes up, the other goes down at the same rate. And then when things increase together, like depth increases, water pressure increases, we call that directly proportional. Yes, Miss Darcy.
I was also gonna say about the bread exploding. My mom made a pizza last night,
Oh.
and you leave it to rise a bit in the oven.
Mm-hmm. Yeah.
It was maybe it.
Oh.
It's not a baking sheet, maybe that big. It was
Yep.
about that big.
Wow.
We took it out and we put our hands on it, and it was pleasantly warm. And then these little geysers of hot air.
Oh, yeah. So let's talk about transmitting pressure in fluids. So who is Blaise Pascal? If you have your phone, we can go for this.
I don't have a phone.
Nobody has a phone.
I can't access the internet.
That's
Yeah, I
okay.
do not have a phone, so
We'll do it together. So who was Blaise Pascal? These are going to be your questions. So in what year was Blaise Pascal born? Everybody take a guess. What's your guess, Eunice? 1867. What do you think? 1950 something?
1867.
1752.
1752, 1623. So we're a ways back. All right. So our next question about Blaise Pascal is, ba-ba-bum, where was he born? France. Do we all agree? He's about, yes, Auvergne, France. He's got a little French flag. I mean, it's kind of a giveaway. All right. How was he educated? What do we think? What do you think? Yeah. How was he educated? What's your guess?
He just like sat in a library and read books.
Read books all day? What do you think?
School.
School? What do you think?
France, like France.
In French? He was a homeschooler. Woo-hoo for Blaise Pascal. Now, here's the thing. Blaise Pascal and his sister were homeschoolers because his father thought they were too smart for the local school and refused to send them.
My big brain.
Woo. All right. How old do you think he was when he published his first
16.
work? 16? 11?
14.
14? 14?
14.
All right, Emma, you're real close. There you go, 16. Outstanding. Yeah, you did. Yeah, 16. You got it. All right, now, next question. Doo-doo-doo. Come on, load it up. Takes a second when I've got the Mentimeter going. Okay, what was his first work about?
A book.
So conic sections, molecular germ theory, or hydraulics. Okay, who votes for conic? Who votes for conic sections? That's like when you, how to do the math for the volume of a cone. Who wants to vote for that? Nobody? How about molecular germ theory? All right, and how about hydraulics? Hydraulics would make sense, right? But he actually published a work on conic sections, and all of the great minds of his age did not believe he wrote it. They thought his father wrote it and put his name on it.
Why does this always happen?
Right? Right? Because he was so young. So in 1642, he invented something called the Pascaline. What do you think it did? Emma, what do you think it did?
It measured pressure.
Measured pressure. What do you think, Darcy?
I think that it pushed something down to make something else rise.
Okay. So what it was, it looked like that. It's a calculator. It's one of the earliest adding machines or calculators ever created.
You mean just like using abacus?
Well, yeah, sort of. So, but you can see as you turn the wheels, do you see these numbers kind of appear here on these rolls? So when he after he invented this for many, many, many years, like a couple centuries, we believed it was the first one. And then we actually found there was one that was invented a little bit before his, but still pretty darn cool. All right, so our next question would be, what was his most famous published work about? And here are your options. Hydraulics and fluid, music and rhythm, arithmetic and geometry, philosophy and religion, and optical theory and light. Darcy, what do you bet?
Hydraulics and fluid mechanics.
Hydraulics, Nico? Hydraulics?
Hydraulics.
Okay, this one's interesting.
Oh, is it like theory?
Philosophy
Optical
and
theory?
religion.
Philosophy
Yes.
and religion. Okay, so here's the guy who we know the unit of pressure is named after him. So we know he has something to do with physics, but we also know he studied conic sections. So that's mathy, right? And now he's writing about philosophy and religion. Do you know what you call the word for a person that is well-educated, well-versed in multiple different areas? Do you know? Well-rounded, yeah. There's a big brain. There's a word called polymath. You ever heard polymath?
Yes, like
It's actually dropped as a lyric in Hamilton at one point. But yeah, a polymath is somebody who knows a lot about a lot of things. And Blaise Pascal was one of those people. All right, so he wrote this work on philosophy and religion. Okay, so the book is called Pensées, or Thoughts, and it highlighted what we now call Pascal's wager. What do you think the wager was? Was it betting on scientific laws, betting against scientific theories, betting on the existence of God, or betting against the existence of God?
betting on the third.
Everybody's going for the third one? All right, y'all are right. Okay, so Pascal's wager is basically, so here's this guy who did physics stuff with hydraulics, he did math stuff with conic sections, then he wrote a book about philosophy and religion. And Pascal's wager is the idea that, well, we don't know if there's a God, but err on the side of caution and act like there is, because if there is, you're good. If there's not, you're in trouble. That's Pascal's wager, right? That's the idea. All right, so in his study of hydrodynamics and hydrostatics, which item did he not invent? So a syringe, a barometer, yeah, never do that, or a hydraulic press. Which do you think he did not? The
Hydraulic
syringe?
press. We
Hydraulic
did not
press?
do the syringe because my dad has informed me that that was not invented by him.
Oh, yeah?
It was invented by a Scottish man.
Oh?
He always drops out at the dinner table. This.
The
is invented
syringe?
by-
Well, he's been given credit for the syringe because he used existing barometers in his experiments. So he didn't invent barometers, but hydraulic press, and he's been credited with the syringe. Now, there are different types of syringe, so maybe that's where your dad's going, but he definitely had one of the first.
He's always-
Okay, so which of these is Pascal's principle or Pascal's law? So when there is an increase in pressure at any point in a contained fluid, there is no increase at any other point in the container. Or when there's an increase at any point in confined fluid, there is a decrease at every other point. Or when there is an increase in pressure at any point in a confined fluid, there is an equal increase at every other point in the container. First, second, or third.
You lost on
Ah,
Third.
it's going to be third. Yep. So what did I say it was called when two things have the same relationship and they increase or decrease together? It was the word proportional. Do you remember? Directly proportional, whereas inversely proportional means one goes up, the other goes down at the same rate. So in this case, increase in pressure at any point in a confined fluid. What's meant by confined fluid? What do you think?
That's the thing, like a jar.
In a jar, in a container. Is there confined fluid, right? Like, is this confined fluid, this air? No, no, no. But if you had it in a container, right? So it's confined, right? Contained. So there's a directly proportional relationship between increased pressure at any point in that confined fluid and equal increase at every other point. Okay. Basically, he's saying if you had a syringe, all right, and you press on the end of it, like you're going to squirt stuff out the front, right? When you do that, you're increasing the pressure through the whole fluid in the syringe, not just that little part you're pressing on, right? The whole, otherwise it wouldn't work. Okay, so in 1661, Pascal is credited with having designed what is perhaps the first. Anybody want to guess? We've already got a calculator. Yeah, we've got a calculator, we've got a syringe, we've got a hydraulic press.
The hydraulic press.
This one's wild. Are you ready? This one's really wild. There's no way you would have guessed this on your own because this is just kooky. A city bus line. No joke. Yep.
What's the city bus
It's called
line?
Carrosse à Cinq Sols, which is like a carriage for 5 people could get in it. And it was a bus line, like he invented the whole idea of this moves here, picks up, drops off, this moves here. Go
That's the
figure.
bus
Uh-huh.
Didn't know what it
Yeah, a bus line.
was.
This guy invented a little everything, right? This is a true polymath, somebody who's all over the place. Okay, now here's the crazy thing. Considering all that he did, he was sick almost his entire life. He was a sickly, kind of physically weak person. So what do you think contributed to his death? Tuberculosis,
All of the above.
stomach cancer, convulsions, or all the above?
All the above.
What are convulsions?
I don't know.
Like seizures.
Oh my
Yep, it was all the above. And so he likely suffered from tuberculosis and stomach cancer, and he experienced violent convulsions the night before his death. And his autopsy also revealed he had a brain lesion. And he did all that in his life, like a spot on his brain that's damaged somehow for some reason. So he had all that craziness going on, and he still invented all those amazing things. Oh, look at this. So how old do you think he was when he died? What do you think?
23.
23,
47.
47. Yeah,
I'll say
that scares me. I'm 47. 60 something.
44.
All right. So he was 39. 39. All of that in 39. Well, his first published work, how old was he? 16. So yeah, he did a lot in not so many years.
My mom's older than that.
Yeah, I am too. Right? Incredible. So where would you find him today? Remember where you find Newton? Where you find Newton where? Do you remember? Yeah, yeah, in France. You'd find Newton in Westminster. We talked about that, right? Okay, so are you going to find him at Notre Dame in Paris? You're going to find him at Canterbury Cathedral, UK, Saint Etienne du Mont, Paris, Basilica de Santiago Compostela, Spain, or Cathedral of Sacred Heart in Virginia. What do you think?
Middle one.
Virginia.
Saint Etienne. Okay, yeah, Saint Etienne du Mont, which is Saint Stephen on the Mountain in Paris. There's his little epitaph. And this is an old drawing of the church when it was built, and this is what the church looks like today. So if you're looking for an incredible polymath, you want to go visit a grave, Blaise Pascal would be one to do. So let's watch a quick Blaise Pascal video. which will recap what I was just saying about him. He's a super amazing dude. Let's see where our volume is going to be. I don't have any idea. Oh, perfect.
Blaise Pascal was a 17th century mathematician and philosopher who made great contributions to both fields. You might have heard of Pascal's triangle? He was born on June 15, 1623. His mother died when he was about 3 years old, so his father moved Blaise and his two sisters to Paris and took charge of educating them. Blaise took to math like a fish to water. While other kids were like, I like girls, Pascal was like, I like comic fiction. His dad worried Blaise would reject his classes, so he banned math in their studies. Blaise took to studying geometry behind his dad's back and made up a lot of his own geometry terms. As a teenager, he started working on calculating machines, known as Pascal's calculators. Over 13 years, he built 20 machines and 50 prototypes, including one of the first mechanical calculators. But it wasn't a huge commercial success. It was cumbersome and it was really expensive. It became more of a status symbol for the rich than an actual machine. Pascal is also credited with coming up with Pascal's triangle. It's basically an addition pyramid. Each number equals the sum of the two numbers above it. This creates patterns along the diagonals and rows. It can be used to solve things like probability, combinations, and exponents. Outside of math, he dabbled in the sciences, invented the hydraulic press and the syringe. Pascal may have been a man of science, but his most famous work was entirely unscientific. He had one of the most unique perspectives on religion and faith, particularly the belief in God. Pascal was by no means the first scientist to question or attempt to prove or disprove the existence of God, but his take was unique in its pragmatism. The way he saw it, like a mathematician, the odds of success were what mattered. If you do believe in God and he exists, you win. If he doesn't, well, nothing lost, nothing gained. So Pascal argued, bet on God. You have nothing to lose. This hedging your bets approach to religion became known as Pascal's wager, and it opened up an entirely new way of thinking about religion. Pascal viewed the world in terms of maximizing benefits in return. So even if you're not a religious person or you take issue with Pascal's wager, you can't deny that Pascal ushered in a new school of religious and philosophical thought. Pascal continued to write on religion and philosophy until 1662, when he died from a stomach tumor at just 39.
Crazy. Stomach tumor at 39. Okay, so transmitting pressure in a fluid. So Pascal's principle is that a change in pressure at any point in a contained fluid is transmitted equally and unchanged in all directions throughout the fluid. If the fluid is not fully contained, increasing the pressure on the fluid creates what? Eunice.
Force pump.
There you go, a force pump, which moves fluid from one place to another. Right. So anybody use mouthwash?
Yeah.
Use
No.
that. Right? Puff out one cheek, puff out the other. Fluid's moving from one side to the other because you're increasing pressure on one side.
I figure out how to do that.
Yeah. We increase pressure on one side, it decreases the other, and then back and forth, back and forth. So that's basically a tiny fluid pump in your mouth. So hydraulic systems. You guys good over there? Okay, so hydraulic systems are designed to take advantage of, Darcy?
Water pressure.
Yeah, Pascal's principle, water pressure, yeah. Okay. So a hydraulic system multiplies force by applying the force to a small surface area. And then the increase of that pressure is transmitted to another part of a contained fluid, which pushes on a larger surface. So you ever seen a hydraulic lift? Looks kind of like that, but they're bigger and they put cars on them. You ever been to like the car dealership and seen the car go whoop, up in the air? That's a hydraulic lift. So hydraulic systems are frequently used in industrial applications as well as in nature. The water vascular system of some echinoderms, such as what, Eunice? Do you know? Sea stars are an example of a natural hydraulic system. Sea stars, sometimes people call them starfish, but they're not fish. They move water throughout their body, and that's how they move. That's their locomotion, is by shifting water pressure within their body. It's pretty cool. And let me hang on, I'm just checking where we are. Okay, good. That's what I thought. All right, so our last one is a video about how that works because it's actually really cool. So this is how a sea star moves, maybe. There we go. All right, so y'all watch this for a sec.
Hello, welcome to episode 3 of 60 Second Zoology. I'm Amy, a zoologist, and in this episode, we're going to take a closer look at the intervascular system of starfish. Starfish are pretty weird in their anatomy, with their anus in the middle of the central disc surrounded by veins. However, there is much more to these weird creatures than first meets the eye. Inside the body of a starfish is a system of tubes called the multivascular system. This is a clever system of hydraulics which gives life to these echinoderms. Water enters this system through an opening with the magic chlorides. It is then distributed around the body through canals which run along the arms and around the central disc. This is all done to operate the tube feet, the funky little appendages that the starfish uses to move around, cling on surfaces, and pass food into its mouth. Safe to say that without their tube feet, starfish wouldn't be able to survive very long. This strange feature is a unique adaptation to the echinoderms. That is the sea stars, the British stars, the sea cucumbers, sea urchins, sand dollars, and the crinoids.
So Pascal is smart enough to take something we see in nature that he probably didn't even know was a thing and turn it into an industrial application. We use hydraulics all over the place, everywhere. Yeah, we're good. So, hi. So yeah, we use hydraulics everywhere all the time. A lot of us, you've probably had, ridden on things that involved hydraulics, used them and never even thought about it. All right, so we have a few minutes. We have about, hang on, listen. We have about 9 minutes, and in those 9 minutes, you can get your breath.